final review problems 9 and 10. Both of these problems deal with orbital motion, and so I want to remind you how orbital motion works. I'll derive the equations of orbital motion, and then you can apply the equations to get the answers to the particular questions that are asked in problems 9 and 10. So what's going on here is that we have some large mass, maybe a planet Earth, maybe planet Mars in another problem. There's the center, and we have some other body that's the satellite that's orbiting that center. And the distance between the centers of those two objects we'll call r. And let's say that the satellite has mass m1, the planet or the large mass has mass m2. Newton's law of universal gravitation says that the gravitational force between those two objects is capital G m1 m2 over r squared. That's the magnitude of the gravitational attraction force between those two objects. So if m1 is set in motion around m2, if it's given a velocity, then it can move in a circular path, and this gravitational force becomes the centripetal force that holds the satellite in its circular orbit. So if we have circular motion, then we can draw a free body diagram for M1. That would look like this. There's the gravity force pointing toward the center of the circle. So that gravity force is the centripetal force that's changing the direction of motion. And Newton's second law says that the sum of the centripetal forces equals mass times centripetal acceleration, and with our sign conventions pointing away from the center is positive, so the gravity force is pointing toward the center, we put a negative sign there. That equals m1 v squared over r, again with a negative sign, because the centripetal acceleration is inward, which is negative. But those two negative signs cancel each other out, and we replace Fg with the full expression for the gravity force. G m1 m2 over r squared equals m1 v squared over r. And the mass of the satellite cancels out, one of these r's cancels out, so we get this expression v squared equals g times mass of the planet divided by r. Now that's one useful expression that relates the speed to the orbital radius and the mass. From this expression, we can also note that v is 2 pi r divided by period. In other words, distance over time. The distance is the distance of this orbit, the circumference of the orbit, the circumference of a circle is 2 pi r, and the time to complete one orbit is called the period, and we use capital T. So if we substitute that expression into v squared, we get 4 pi squared r squared over t squared is g m2 over r. And you can move this around a little bit and get this relationship that t squared equals 4 pi squared over g times mass of the planet times the radius of the orbit cubed. All right, now with these two expressions, we can answer the questions in those review problems. So in problem 9, we are given the orbital radius and the period. And from that, we want to find the mass. So the situation here is that you're given the orbital radius and period of a moon of planet Mars, and from that you can determine the mass of Mars. So for given this information, you can use this equation, do some algebra, and solve for m2. You've got all the stuff you need from that equation. Turn it around via algebra and solve for m2. You can figure out the mass of Mars. And that's one technique that astronomers do to figure out the mass of planets and stars that they observe. You can watch a satellite orbit some body, measure the radius and the period, and determine the mass of that object. So that's a way we can determine Mars's mass. In problem 10, we're given the mass of a satellite. So we're given m1, and we're given the radius. The way that this radius is expressed, it says it's a height equal to the Earth's mean radius. So that means that this distance r is the Earth's radius plus another Earth's radius. So it would be 2 times the radius of the Earth. So that's the value you can use for radius in that problem. And given this information, find the satellite's orbital speed. So A, find the speed, and you can find that using our equation here for speed. You're allowed to use, you're allowed to look up the value of the Earth's mass. So we find V using this equation. And in part B, we find the period, and you can find the period using this equation. And in part C, find the gravitational force acting on the satellite, meaning calculate this value of Fg from Newton's law of universal gravitation. So plug in the numbers into this equation. So all of these satellite orbit questions that you might encounter use this, and this. And you might have to do some algebra to rearrange those equations, but they all come from this Newton's second law analysis of circular motion, where the centripetal force is the gravity force. And any question that you might get asked is just some variation on this analysis, and you can figure